Hi everyone. So this was your test 3. So I'm going to just go over a few of the problems, the ones that seem to give more of you some trouble. I mean, overall, the test was pretty good. So this is for, for some of you that just wanted a quick explanation of some of the solutions. But by the time you're reading this, the solutions will have been posted, so you can just look at the solutions as well. So number one was pretty much okay. It's by and large most of you got number one. So I'll start with number two, where I gave you the derivative of a function, right? So this is f prime of x. I just wanted to make that clear. And again, part A, I think most of you got just to find the critical numbers. So to find the critical numbers, you don't have to take the derivative, right? You already have the derivative, so you just set this equal to 0, and most of you did that just fine. Since it's already factored, of course, that made it easy. So for x minus 4, you get x equals 4. And for this, you get x squared equals 5, which is x is plus or minus the square root of 5. And yeah, a few of you missed the negative, right? There are actually 3 critical numbers for part A. So negative square root of 5, positive square root of 5, and 4, right? I don't think anyone put negative 3. That's just the coefficient, right? So that's not a critical number. And then in part D, I just wanted the sign chart. So just like I did in the video, I drew a sign chart for the derivative, and I just marked off the critical numbers. We have negative square root of 5, positive square root of 5, and 4, and that's where the derivative is 0, right? And then, so how do you get the signs? Well, the easiest way is just plug in into the derivative just some number in this interval. Let's plug in 5, right? That's bigger than 4. So if you plug in 5, you just get negative 3. And then, so 5 squared is 25, minus 5 is 20. And 20 squared is 400. And then 5 minus 4 is 1. So this is just going to be negative 1200 or something. And of course, we don't really care what the number is. We just care whether it's positive or negative. So you can see the only negative sign here is with the negative 3. So for 5, it's just going to be negative here, right? And then what happens when you plug in, say, 3, which I think is bigger than square, right? Square root of 5 is 2.2 something, 2.3, somewhere around 2.2, 2.3. So 3 is bigger than that, right? So if you plug in 3, well, you're going to get a positive. Now, how did I know that without showing the work? Well, because the exponent here is an odd number, and when you have an odd number, the signs automatically alternate at x equals 4, right? But if you don't believe me, just check, right? You get negative 3, and you get 9 minus 5, 9 minus 5 is 4, 4 squared is 16, and then you're going to get 3 minus 4, which is negative 1, so you get a negative times a negative, which is positive, right? So between negative square root of 5 and positive square root of 5, you get 0, and if you plug that in, you're going to get positive. And again, I knew that from the exponent here is odd for both factors, right? You have a factor of x minus the square root of 5 and a factor of x plus square root of 5, but they're both squared. So because the exponent is even, right, you're just going to get a negative. But officially, it's, negative 3 times 25 times negative 4. So I think that's negative 300, but it is negative. It's positive. Positive 300, right? So negative times a negative. It's positive 300. Oops. Sorry. Positive. And then same thing here. You plug in negative 3 and you still get a positive, right? So once you have the sign chart, and I already asked a lot of questions on the test. I didn't want to ask, where's the function increasing, where's it decreasing? But based on this, you can say that f is increasing on the interval from negative infinity to, 4. And then it's going to be decreasing from 4 to infinity. Right. Yeah, but again, that wasn't part of the question. So if it's increasing then decreasing, you know that x equals 4, is a relative maximum, right? So that comes up, oh no, that doesn't come up, never mind. I'm thinking of a different question, right? Anyways, part C is the second derivative, and for the second derivative, well, you have to take the derivative of the first derivative. And a lot of you multiply this out, and while that's okay, you really should know the product rule. And if, in fact, this is a triple product, you have -3 times x squared minus 5 squared times x minus 4, but the -3 is a constant, right? So leave the -3 alone and just multiply first times the derivative of the second. So that's just going to be x squared minus 5 squared. And then the derivative of x minus 4 is 1 minus 0, right? And then plus second, which is the x minus 4, times the derivative of the first. The derivative of all of this, well, power rule, so you're going to get 2 times x squared minus 5 to the 1, and then times the derivative of x squared minus 5 by the chain rule, you get 2x. Okay, so notice that you get a common factor here of x squared minus 5. So I'm going to pull that out. So -3 times x squared minus 5. And then what's inside the brackets here, you get another x squared minus 5 to get x minus 5 squared. And then plus, so this is something you probably will want to multiply out. You get 2 times 2x is 4x times x minus 4. Sorry, that's an x there. Yeah. Right. And then we should expand all this out in the brackets here. So -3 times x squared minus 5 times, so x squared minus 5 plus 4x squared minus 16x. And now, when you simplify all that, you get 5x squared minus 16x minus 5. Okay, so yes, and you can expand this out. I did that in the answer key, but it's really better if you leave this alone at this point, because in part D, you want to find the possible inflection points, right? In other words, you want the sign chart where the second derivative is positive or negative. And to do that, you really have to set this equal to 0. And when you set the first factor equal to 0, you still get negative square root of 5 and positive square root of 5. Right? So those were also critical, those were also critical numbers, but they can also be possible inflection points as well. Okay, and then you solve this, 5x squared minus 16x minus 5. You solve that using the quadratic formula. And I forgot what you get. You get some horrible number here. You get, let's see, 8. Oops. So you get 8 plus or minus the square root of 89 over 5. Okay. And so your sign chart in part D it's going to be a long one. So the smallest number's negative square root of 5. Then you get this number here. And I never bothered figuring out the decimal approximation for it. Although I probably did to know where it lands here. Yes, then you get positive square root of 5. And then the biggest one is 8 plus the square root of 89 over 5. Okay, so remember we're making a sign chart for the second derivative because we want to know where is it concave up and concave down. So you notice that all the exponents here are just going to be 1s at this point if you factor this out using radicals here. So the signs are just going to alternate. And the one on the right here is going to be, so this is all positive, but you still have the negative 3. So that makes this negative, that makes this positive, that makes this negative, that makes this positive, and negative. So all the signs alternate because there's no even multiplicities. There's no even exponents, right? So that gives us the sign charts. And then we can answer part E, which was, where is it concave up? Well, wherever you have a positive, right? So it's going to be concave up from negative root 5 to, and again, I didn't care if you put the decimal here, that's fine. And then union from, again, square root of 5 to this number, 8 plus square root of 89 over 5, or its decimal equivalent. Again, you're going to round, I mean, these are irrational numbers. You're going to round to, 3 or 4 decimal places, which is fine. And obviously, then for part F, where is it concave down? Everywhere you see a negative. So from negative infinity to negative root 5. And then from this number, I don't know why I'm bother writing this down. It's all in the answer key, right? And then this number here, 8 plus square root of 89 over 5 to infinity, right? Okay. Oh, so where do you have inflection points? Or just the x-coordinates, right? So everywhere the sign changes, so all 4 of these. So I'm just going to write them all at once. Plus or minus square root of 5, and then 8 plus or minus square root of 89 over 5. You could have done that. So there's 4 inflection points, right? 4 inflection points. But only one maximum, and that was at x equals 4. So negative root 5 and positive root 5 are not maximum or minimum points, but they are inflection points. So I hope that helps for number 2. Okay, so 3A, 3B, most of you got that. 3C, and again, a lot of you got it, but some of you didn't, so I want to make this clear here. So you can take the 4 over 5 out, right? A lot of you did that. So this is 4 over 5 times the limit as theta goes to infinity of cosine 3 theta divided by theta, because I took the 5 out. And you realize that you have to multiply top and bottom by the 3 here to match what's in the bracket here, right? So I'll just bring the 3 on the outside, right? Oh, you know what? Never mind. This is if you're taking the limit as theta goes to 0. And I think some of you did that too, but it's so easy to make that mistake here. Yeah, we don't have to do any of that here. That's totally not necessary. So what's this limit here? Well, again, most of you got it. It's 0 because the numerator is bound between negative 1 and 1, and the denominator just gets bigger and bigger, right? In other words, you're using the squeeze theorem, right? So this is negative 1 over theta is less than or equal to cosine of 3 theta over theta, which is less than or equal to 1 over theta. And, a lot of you were a little sloppy here, but that's fine, right? This goes to 0, this goes to 0. So by the squeeze theorem, this also goes to 0 as well. And so 4 over 5 times 0 is 0. Right. So either write that it's by the squeeze theorem, or make sure you put the inequalities, or both. That would be better. So that was C. And then D, yeah, I think I did one like this in the videos. I'm not sure, though. But there was one very similar to this in the book, right? And the idea is you multiply by 1 over x over 1 over x, because the biggest power in the denominator is not x squared, it's the square root of x squared, which is x. And before you say, well, what happens if you're going to negative infinity? Yep, So x is really negative x squared for x less than 0. So that's going to be important in a minute. So, yep, so the next step is to turn these, right, or the numerator rather, into, so keep the limit, into 2 plus 1 over x, right? And the 1 over x goes to 0, divided by, so now you can incorporate this inside as long as you take out a negative, right? This negative up here. So this will just be 3x squared over x squared minus 4 over x squared, right? And so, well, I'm getting ahead of myself here, right? So the negative is going to be in front here. Oops, because you're going to negative infinity. So, yep, 2 plus 1 over x divided by the square root of 3 minus 4 over x squared. Now you can use the property that anytime the numerator is a constant and the denominator contains some power of x, well, again, some rational power of x, right? And 1 and 2 are rational numbers, so that's fine. Yep, that these just go to 0. So what are we left with here? We're left with the negative in front and then 2 over the square root of 3. Right? And I think I've told you in class many times, I don't care if you don't rationalize the denominator. But if this were in the book would write it as negative 2 square root of 3 over 3. So just at least know that you can convert from one to the other. You just multiply top and bottom by square root of 3 here to rationalize the denominator. But either way is fine. And then 3e. Now 3e was the challenge problem because I don't think the book really did anything like this, although there were some in the homework like this. This was a very tricky one. So if you got it, you know, congrats. It's, you know, this was a hard one. You know, they can't all be easy, right? So A and B, I think, were I shouldn't say easy, but they were routine. They were routine. Okay, so x is going to infinity here, and this is x minus the square. I'm just copying it down for no reason. So x minus the square root of x squared minus 3x, right? So the trick is, and again, it's in the homework, the trick is to multiply numerator and denominator by the conjugate, right? X plus the square root of x squared minus 3x over itself. Yep. I mean, we've seen this before, right? Even in chapter 1, we've done problems like this where we've had to sort of rationalize the numerator when we were finding limits. So this is nothing new, but we haven't done it in a while. So you may have forgotten the conjugate trick, right? So when you expand all this out, the numerator becomes, right, x times x is x squared. And the reason for doing the conjugate is so that the outside plus the inside add up to 0, and then you just get minus the square root of this thing squared, which is just x squared minus 3x, right? And the denominator is just 1 times x plus the square root of x squared minus 3x, right? So notice what happens in the numerator when you get rid of the parentheses here. Actually, yeah, well, okay. So you get rid of the parentheses, and then you change the negative 3x to a positive 3x. So change that. So that becomes a plus 3x, and x squared minus x squared is then 0. So then you just get 3x divided by x plus the square root of x squared minus 3x. And even now, we're still kind of stuck, right? Because you still get, you know, it looks like infinity over infinity, right? It's still an indeterminate form. So one more trick, and I shouldn't call it a trick, it's just a technique that you get used to. You multiply by 1 over x, right? The biggest power in the denominator is x. So what you end up with here is just 3 divided by, right? So it's 3x over x, right, is 3. And then this will be 1 plus, and then when you bring this inside, now in this case, because you're going to positive infinity, you can just do x squared minus x squared is 1, and then minus 3x over x squared is 3 over x, right? So finally, now you take the limit as x goes to infinity, this goes to 0, which means you're just going to get 3 in the numerator and 1 plus the square root of 1 in the denominator. Well, that's just 3 over 2. Or, if you prefer, 1.5. I was not picky about that, but 3 over 2. So that was 3e. Sorry, 3e. Okay, and then number 4 is the only one you really had to graph. So I gave you this function, x cubed minus 16 all over x, and you're asked to find the vertical asymptotes. Well, by now that should be pretty easy. You just set the denominator equal to 0, and notice the numerator is not 0. So of course you just get x equals 0. So there's really nothing to show there. That should be obvious, right? And then for part B, the X-intercept, so that's where the numerator is 0. So, yep, part A, you set the denominator to 0, and then part B, you set the numerator equal to 0. And even though this is a cubic equation, it's pretty simple, right? You just add the 16 to both sides and then take the cube root. So x is going to be the cube root of 16, or 2 cube root of 2. I wasn't picky about that, right? So it's an x-intercept, right? It's a point on the graph, which, when you graph it, you should make sure you have that point there. And I think I did approximate this one. This was, oh no, I didn't. All right, I think it's about 2.5, right? 2.5, roughly. So again, to graph it, it's good to know. Okay, so part C, slope of the tangent line at the x-intercept. So at x equals, cube root of 16, any way you want to write it is fine. What's the slope of the tangent line there? So for that, you need the derivative, right? You need the derivative. And you can use the quotient rule. That's not a problem here. But before we do that, you might want to rewrite this as just x squared minus 16x to the negative 1, just to make it easy, right? So you get 2x minus 16 times negative 1 x to the negative 2. So that's really just 2x plus 16 over x squared. And so when you set that equal to 0, you're going to get, I think, 2x cubed equals negative 16, or, oh, I'm sorry, that's part D. Oh, okay, hang on. All right, so I'm doing part D, actually. Part D. So, yeah, for part D, you want the critical numbers, right? So this gives you the critical numbers, which is just negative 2, right? Cube root of negative 8 is negative 2. All right, so that's part D. That's the critical number. So let's go back to part C then, right? So this is the derivative, right? In fact, let me rewrite it so we can use that. So 2x plus 16 over x squared, or if you prefer, you get 2x cubed plus 16 all over x squared, either way. So you're just going to plug in this number, cube root of 16, into the derivative. And maybe it is easiest in this form because the numerator is just 2 times 16 plus 16 divided by, well, the cube root of 16 squared. So that's going to be 16 to the 2/3. So the numerator is, I think, 48. And the denominator, so there's a lot of ways you can clean this up, but you really should simplify this a little bit. I mean, look, I wasn't picky, but, you really should know how to simplify this, right? So this is just going to be 2 to the 2/3 times 8 to the 2/3, and 8 to the 2/3 is 4. So this is 4 times the cube root of 4, and 48 divided by 4 is 12. So you get 12 divided by the cube root of 4, which when you rationalize the denominator, which again, you don't have to, but it does help, you get 12 cube root of 2 divided by the cube root of 8, which is 2. So you should end up with 6 times the cube root of 2. And so that's the answer I'm looking for. The approximate was 7.56. But, you know, again, that's fine. So you can round as well. It's not a big deal. But that's the slope. Remember, I didn't ask for the equation of the tangent line. So you don't have to find the equation. Some of you, I guess, were trying to do that because you were doing, you know, the point slope form here. Not necessary. I didn't ask for the equation of the tangent line, right? Just the slope. Okay. And then part D I did already. Part B is the critical numbers, and there's only one, x equals 2, negative 2. So part D, x equals negative 2, is the only critical number. And then part E was to find all the relative max and min points. So relative minimum and relative maximums. So, well, there's only going to be one because there's only one critical number, right? So is it a maximum or a minimum? Well, you can do the first derivative test or the second derivative test. I guess most of you did the first derivative test. So where was the, well, here's the derivative up here, way up here. And so just plug in a number bigger than negative 2. 0 would be nice, but 0 is not in the domain, right? So you can't plug in 0. So maybe plug in 1, and you get 2 plus 16 is 18. 18 divided by 1. So that's definitely a positive. And if you plug in something less than negative 2, say negative 3, well, what do we get? I guess I should plug that in then. So you're going to get, I'm going to use this version here. You're going to get negative 6 plus 16 divided by 9. Well, I can tell that's negative, right? 16 divided by 9 isn't even 2, so negative 6 plus 2 is negative 4. So it's probably a little bit less than negative 4, but that's fine. It's negative. So, right, so if you're going from a negative to a positive, it means you have a minimum. So we have a relative minimum at negative 2. Oh, I did ask for the point, right? So negative 2, and then plug in into the original function. You got to go way back to the original function up here, right? Plug in negative 2, and I think you get positive 12. So yep, you had to find both the x and the y, right? Because I asked for the relative minimum point. A point is two numbers. It's an x and a y. All right, and then part G is the graph, and you know, you can look at the answer key. I'm not going to try to graph it here. It's going to be way too sloppy. Oh, you know what? A lot of you were sloppy too, so whatever, it's fine. So notice I didn't even give you, you know, your scale here. So you're supposed to put a little bit of a scale. And then, actually, I'm not going to bother with the y scale for reasons you'll see in a second, right? So remember, the cube root of 16 was about 2.5, so that's the x-intercept right about here. And then negative 212 was your relative minimum. Oops, not 12, 2, negative 212. Right, and x equals 0 was your vertical asymptote, so make sure you don't cross that. And then this goes up pretty steep as well here. There's no slant asymptote. I didn't ask for that, but what happens is that you basically, this hugs the graph of y equals x squared. So this becomes a curve. And the same thing happens here too, right? Okay, it's not as steep. I mean, it should be steeper here, right? Should be a little bit steeper. And then what happens is it kind of goes back up. So there is an inflection point somewhere in here, but again, I didn't ask for that. So make sure you have the x-intercept right. Oops. Cube root of 16, about 2.5. And the local minimum, negative 212, and that's the basic shape of the graph, right? Oh, and the vertical asymptote. A couple of you are crossing the asymptote, and if you cross the asymptote, that's bad, because then it's not an asymptote, right? And then number 5, so this was an optimization problem. So we have a cylinder, and over here on the right is my really sloppy cylinder, but you know, it's the best I can do. It's drawn on the test, obviously. I just didn't copy that down. So we have a cylinder constructed out of a material that cost $1 per square meter for the tubular section. So that's this part here, right? And then $3 for the discs. Now, I know I said top and bottom, but unfortunately this is sideways, right? So the discs are right and left. But, you know, you could have asked if you had a question on that. So top and bottom, I mean, here it is. Now it's top and bottom, right? So just turn it sideways. Anyways, the volume, of course, I gave you. The volume is just pi r squared L. And it has to be 80 cubic meters. So most of you did the correct thing and divide by pi r squared to solve for L. So L is really just 80 divided by pi r squared. Right? And then you want the cost, right? So we need the cost function, which, you know, I called C of L, I guess. Or no, C of R. This is going to be in terms of R. Anyways, it's just the cost. It's just C. So how much does it cost? Well, let's do the top and bottom, right? Or the right and left, the sides, right? So we have 2 of them. So they're 2 discs, 2 pi r squared. That's the total area of both discs, right? Or top and bottom, either way. But it's $3 per square meter, right? So this is the number of square meters multiplied by $3 per square meter. And then for the tubular part, the area of that is 2 pi r L. I didn't write it down, but you know, you can look it up. You have the book. Obviously, you can use the book. You know, I mean, look, it's when you take a test in class, of course, it's, you know, closed book, closed notes, everything. But, you know, I mean, I wrote these with, you know, with the idea in mind that, you know, you should do it that way. On the other hand, I can't really stop you from looking in the book. So this is the surface area of a cylinder, of course, without the 3 here. And if some of you did some of you minimized the surface area, which means you just forgot the 3 here. But you had the right idea, so you got, you know, I think you got 8 points out of 10 just for doing that. In any event, this is so let's simplify this. This is 6 pi r squared plus 2 pi r L, and that's the primary equation. This is the primary equation. This is the thing we want to minimize. But in order to write it as a function, you have to substitute for L here this expression up here, right? So plug that in for L, and when you do that, your C will now be a function of just R. So you're going to get, let's see, 2 times 80 is 160 times pi r, but it's going to be divided by pi r squared. So the pi's cancel, and then one of the r's cancel. So I think you just get 6 pi r squared plus 160 divided by r. Okay. So now it's totally just a function of r, which means we can take the derivative. So you do derivative of c with respect to r, or if you prefer, c prime of r. And you're just going to get 12 pi r minus 160 over r squared. You set that equal to 0. And let's see, if you multiply by r squared, you're going to get 12 pi r cubed minus 160 equals 0. You add the 160 to both sides. and then divide by 12 pi. So you're going to get r cubed equals, so 160 divided by 12 pi, well, that's just 40 over 3 pi. And then take the cube root. I know there were quite a few cube roots on this test. Sorry about that, but that's, nothing wrong with cube roots. So cube root of 40 over 3 pi. And your calculator will tell you that that's approximately, 1.62. And a lot of you got the correct answer, right? You got the exact answer, and you probably just put it in your calculator wrong. So you got the wrong number here, and so I had to take a point off for that. But you might probably just use your calculator, and you might have multiplied by pi instead of dividing by it. I don't know. But 1.62 is what you should get, rounded to 2 decimal places. Okay. And so we're rounding to the nearest cent, right, for the cost function. Anyways, so you can plug that into the cost function at this point, and that gives you the minimum cost. Oh, I asked for the length as well. Well, there it is, right? So 80 divided by pi, and then 1.62. It's fine to use the approximate at this point. So this will be 9.71 approximately. So 9.71 meters for the length. And now for the cost, right, you're just plugging in the 1.62 into this. So obviously if you got the radius wrong, you got everything else wrong. Squared. And then plus 2 pi RL, so R was 1.62 and L was 9.71. So that should come out to $148.23. Okay, very expensive cylinder. So it's made out of, I don't know, some very expensive metal or something. It's maybe made of gold, I don't know, but it's an expensive cylinder, right? And it's a big one, right? 9 meters is, close to 30 feet, I think. So it's like a tank. You're constructing a big cylindrical tank. And so, yeah, in that sense, it's not surprising how much it costs to make one of those. And then number 6, this was also an optimization. Again, if this were an in-class test, I probably would just give you one of these. But, I think it's, since you had a long time, reasonable to give you 2. And the previous one was a minimize problem. This is a maximize, so one of each. And, so consider the line segments with the X-intercept at A and the Y-intercept at B. In the first quadrant, using the techniques of optimization, show that the shaded rectangle here has area AB over 4. And, part of it is that I drew the rectangle to scale. So it's, if you did this right, you should have been able to at least guess that, because this rectangle here, sorry, let's try that again. Not easy. So it's just not easy to draw a vertical line on my tablet here, but okay, there we go. So you can see what's going on here, right? This and this is just 1/4 of the area. This big rectangle has area A times B, so this is just 1/4 of it. So I drew it to scale, although I didn't say that, but that's, that made it easy to see here. But again, that's not the question, right? The question is to use the techniques of optimization, so we have to use calculus here. And so the hardest part was to figure out the equation of this line. This line right here. This line here. And why do I need the equation? Well, because we don't know where this is going to end up, right? Like I said, I drew this to scale, But, you know, your rectangle could be this, right? Right? Maybe that's the bigger rectangle, right? So this is, we'll just call this x and y here. So we need the coordinates of this point, x, y. So we need the equation of the line, right? So before we get the equation, the slope should be obvious, right? Slope is rise over run. So it's going down, it's negative b over a. And then to get the equation, right, y equals mx plus b. So m is just negative b over a times x. And then, well, lo and behold, I gave this the right name. It is b. That's the y-intercept, right? So this is the equation of this line. Now we want to find the area of the rectangle. The area is just x times y. But again, that's a function of two variables, x and y. That's our primary equation. This is the secondary equation. You just replace y with negative b over a times x plus b, right? Just plug that in for y here, same y as this, right? And, you know, well, at this point it's a function of x. You could use the product rule, but in this case it's probably easier just to multiply it out, right? So that's my function of x, and this tells me the area of the rectangle with width x, or maybe I should say length x. Right. And it's just a quadratic function, so taking the derivative, setting it equal to 0, no big deal here. So you get negative 2b over a times x plus b, and then when you set that equal to 0, you just solve for x. Remember, a and b are just numbers here, right? X is the only variable here. Although a and b do vary, of course, but x is what you're solving for. So you're going to get negative 2b over ax equals negative b. And then when you divide by b, well, I just did everything all at once here, right? I multiplied by negative a over 2b. So negative a over 2b. And so x is just going to be a over 2, right? Because the b's cancel, the negatives cancel. So a over 2, which again is not a surprise because it's right in the middle. It's halfway between 0 and a, right? And then to find y, you just plug in x equals a over 2. So the a's cancel, and you just get negative b over 2 plus b, which is just positive b over 2. So of course, the y-coordinate here, the y-coordinate right here is just b over 2. Not surprising, because that's the way it's drawn, halfway between 0 and b. And yeah, right here, this x is, a over 2. So, of course, the area of that rectangle is x times y, which is a over 2 times b over 2, which is ab over 4. And that's what we wanted to show, right? Now, there's one subtle point here, and this I didn't ask about this in the previous problem, and I didn't ask about it here either. But remember, the question is to maximize the area. And when you solve for x, this a over 2 here, that's a critical number, but it doesn't tell you if it's a maximum or a minimum, right? Or possibly neither. So how do we establish that this really is the maximum area and not, say, the minimum area? Well, one is to look at the, well, I messed the graph up here, but to look at the graph, right? Obviously, you can slide this x here way over here, or maybe let's do it way over here, make y very, very tiny, right? And so you can see you have a very long rectangle, but it's so short that the area is, you know, really small, practically 0. So, yeah, so from the picture, it should be obvious that this is the maximum area. But the easiest way is to use the second derivative test. So if you take the second derivative, well, where's the first? Oh, here's the first derivative. Yep. You take the second derivative, you just get negative 2b over a. And when you plug in your a over 2, it doesn't matter what you plug in. It's just negative 2b over a, which is clearly negative. Oh, we know that because A and B are positive, right? It's in the first quadrant here. So A and B have to be positive, obviously, which means this is negative. And if the second derivative is negative, that means it's concave down. At the critical number, that means you have a maximum. So this, right, that just verifies this is a maximum area. But I didn't tell you to do that. I mean, usually I would say verify that this is a maximum. Yeah, I wasn't looking for that. I'm mostly looking for, can you get the equation of the line, because you needed that to get the function area as a function of just x by itself. And that's an x, yeah. So that's number 6, basically. It's a little abstract because the a and the b here could be, anything. Once you fix a and b, then this is the answer. Now, there was a problem like this in the book where they gave you actual numbers here, like 0, 0, 3 and 5, 0 or something. And, they probably even gave you the equation of the line, too, to make it easy. But so I wanted to make this just slightly more challenging and a bit more abstract with the A's and the B's. But otherwise, I think a reasonable problem, not a, complicated one. Okay, finally, 7C. So this, I have to apologize. So this is my mea culpa here. This is a typo. This was not supposed to be the problem. So the short of it is everybody got full credit for this. A, because it was, it was not the problem I intended. And so the problem, as intended was much more complicated. One that some of you already knew, which is great. But obviously I didn't expect you to know that because we didn't get to that. So technically we shouldn't be able to do this until chapter 5. However, yeah, so here, this was the problem that it was supposed to be. And I'll give you sort of a second to figure it out. I just had the 2 in the wrong place. The 2 was supposed to be downstairs with the sign. Right, so that's the problem I intended to give, which I think would have been reasonable because you know how to do sine, and then this was supposed to be cosecant times cotangent, right, which of course, you can look up. So this is negative cosine and then minus cosecant plus c. Oh, a few of you forgot the c's. Right, so that's what the problem was supposed to be. As it was written, however, so there's a couple ways of doing this. Most of you got a common denominator here and wrote this as sine squared plus cosine squared over sine, which is perfectly good way to do it. That's probably how I would do it. And so you just get 1 over sine, which is cosecant, without the cotangent, right? So you want to integrate just cosecant. And of course, we didn't do that yet. So that, that made this essentially impossible to do as it was written. But a lot of you know the answer already. And so officially, you'll see this in chapter 5. This is negative natural log of cosecant theta plus cotangent theta plus c. So if you got it, awesome, right? I mean, look, again, you can look this up in the book, right? It's on the front cover. It's one of the, inside the front cover. So that's the best way to do that. Yeah. So again, everybody got full credit for this, and besides, it was already extra credit. So a lot of you got that free 5 points for extra credit. So again, I'm really sorry if you struggled with this, if you did it 10 times and you still couldn't figure it out. Yeah, you weren't supposed to. That's all it is. And I really feel bad because some of you actually emailed me and said, well, wait a minute, don't you get this integral here? And I don't know, I don't think we're supposed to be able to do that. And you're absolutely right. And I might have said, no, it works out perfectly fine because I was thinking it was this. I was thinking that should have been what you got. But that's because I had the 2 in the wrong place. So again, mea culpa. That was a typo. And, but I think I made it right just by giving extra credit. And thankfully, it was the very last problem. So after a very long and tedious and agonizing test, I think a lot of you just gave up on that, and that's perfectly fine. So that made this by far the hardest problem because it's not one that you should have been able to do at this point in time. But that's not to say that the previous problems weren't easy either. So overall, I think a pretty good test, and so that's sort of the level of tests I'm going to give for test 4 in the final. So I hope that helps.